Good morning, good afternoon, or good evening, depending upon where you are. We would like to welcome you to this session on emerging pollutants and groundwater. We have another number of exciting speakers coming forward. I'd like to, first of all, remind all of our speakers that this session is being recorded, and please try to keep to time. We invite you to submit your questions in English for those that are watching via the Q&A button. You can find this button at the bottom of your screen. We'll try to address the questions as much as possible after the talk or in the Q&A session at the end of this session. And you'll only see each question once it is answered either verbally or in writing when they'll be displayed for everyone. We have a huge audience, so I don't know if we're going to have enough time to actually answer all the questions live, but we will collect all written responses from presenters to place in the conference website following this event. And hopefully the presenters will try to type in responses at the end of each one of their talks. Please note that the chat box is disabled during the session. However, we ask you to keep out an eye for useful messages in the chat box that may be shared by the organizers for each one of you. You have the option of switching on the automatic subtitles at the bottom of your screen if you're having hearing difficulties. And if you experience any technical problems, please Google Zoom Help Center or online.conference at IWRA for assistance. I would like to also welcome a co-moderator and rapporteur for this session from the IWRA. And we'd like to kick off with a joint talk by Waseem and Akil, who will be presenting landfill site selection and bioremediation of emerging contaminants in groundwater. And thank you very much, and we look forward to your talk. Thank you.
Good morning, everyone. My name is Waseem Raja. I am joined by Mr. Akil Gupta. I am a Ph.D. student at the Indian Institute of Technology, Jammu, and Mr. Akil Gupta is a project officer working here in the institute. So together, we are here to present our work on landfill site selection and bioremediation of emerging contaminants in groundwater. So wasting no time, how do I change the slide? Okay, thanks. So here in Jammu, if we talk about India, we are a developing country and we are the second largest population in the world. So we generate a huge chunk of this solid waste in our country. And with solid waste comes its management. And most of the solid waste ends up lying in unengineered landfill sites. And what happens there is that this solid waste now turns into leachate and percolates into the ground, which may eventually lead to groundwater contamination. And these cases have been reported in the country in the past as well as in the current years. So here in our study, what we have done is we have used some modern approaches like GIS, MCDM, and other statistical data to check which place would be a suitable place to create an engineered landfill site where there would be the least percolation, and where the percolation has occurred, where the contamination has occurred, we will collect that water and we will try to treat that water biologically with the help of algal bacterial cultures. Next slide, please. Yeah. So if you look at some statistics, here in India, every day a person generates 0.5 kilograms of waste, which most of this waste, like if you look at the statistics, more than 60 to 70% of this waste, it ends up into the landfills. Most of these landfills are unengineered landfills. And from these landfills, there have been cases where it has turned into leachate and then contaminated the groundwater table. And in continuation to that, there has been contamination which have been reported from various cities in India, like Ghaziabad, Panipat, and then some cities from Gujarat, where there has the contamination due to leaching of heavy metals like iron, copper, nickel, mercury has been reported. Next slide. Yeah, thank you. So here the emerging contaminant of our concern is PFOA. That is nothing but perfluorooctanoic acid. The PFOA, it is a man-made, you can say, an additive which we use in plastic things, some non-coating kitchenware, etc. And somewhere it finds its way to the wastewater stream. And the permissible limit in some of the developed countries like USA, Canada, and Germany, it has already been defined. Whereas country, a huge country like India, uh, the limits have not been defined yet. So if you look at the problems which are caused by the PFOA, it has some serious problems which include cancers, liver damage, thyroid problems, and a change in cholesterol. And it can cause major changes in the body during the pregnancy in women. Next, please. So here, Mr. Akil will explain what is our study area now.
Yeah, thanks, Mr. Waseem. So without wasting a minute, I'll continue. Nowadays, one of the major challenges for waste management system is to manage the large amount of waste. Like in Jammu city, 400 to 450 metric ton of waste is disposed of at the dumping site. So with roughly 20 to 30 ton recovered by scavengers, or you can say rag pickers. In the city, trash storage at the source is not systematic. So in the city, there is nothing, I would say, just dumping. As a result, the whole area or region around the dump is filthy, smell bad, and constitute major health and environment risk factor. So these are the potential criteria for selecting the landfill sites among the alternative. Please change the slide. Yeah, these are the governing criteria, potential criteria for selecting the landfill site among the alternatives, including the key governing factors and socio-economic parameters. So in our study methodology, we used multi-criteria decision making, and decision making, as you know, is an important part of the waste management. And efficient decision making helps in achieving the objective, ranging from landfill site selection to the waste collection and transportation route. So it is a modeling and mathematical tool to deal with complex problem in engineering. It consists three phases, namely first we define the context, second governing the criteria, and third the alternative. So multi-criteria decision making can be done by using the tool, analytical hierarchy process, analytical network process. It's one is comprise ranking method. So for our study, we use analytical hierarchy process. Analytical hierarchy process is a scientific technique for analyzing the multiple consideration to arrive at the optimum decision or result, or I can say AHP involve following steps. First one is we have to identifying the goals, weighting each of the criteria, and then the alternative. Second one, we have to develop a pair-wise comparison matrix and check for the consistency. Third one, derive local priorities for the alternative. And the last one, overall priorities, final model synthesis, and we have to make a final decision on that. Yeah, please change the slide. Yeah. So these are the landfill characteristics for the selecting a suitable location. Let's see, the present aim of the study to choose the best location for constructing engineering landfill. Since the identification of landfill site, is a very critical issue, which involves multiple considerations regarding pre-existing land use dynamic as well as the nature potential effect on landfill by geological, hydrological, social economic factors. Yeah, so these are the landfill site characteristics. The total size of the property, we selected two landfill sites at 90.5 acres and other one is 7.5 acres. So we consider 11 potential factors like groundwater depth, land use, primary crop in the study region, nearest highway, nearest railway station as per the CPC, as per the Solid Waste Management Handling Group 2016. So we consider all the 11 potential criteria. Yeah, please, next slide. So based on the selected criteria, we developed a pair-wise comparison matrix. The weight of each criteria is developed by using eigenvector and eigenvalue. The eigenvector so developed also shows the relative weight of each criteria. The principal eigenvalue is calculated through the summation of products of eigenvector with the sum of columns of the pair-wise comparison matrix. Then we have to, as I say, that we have to check the consistency for this. So consistency is done by using the relation by the ratio of consistency index upon ratio index. So in our study, consistency ratio was found 0.0405. So since this consistency ratio is less than 1, so this show pairwise comparison matrix is fairly consistent. Next slide. Then, yeah, as you can see, the third objective is then the local priorities of the alternatives. Site 1 and Site 2 are developed. As you can see, it may be noted that each of the criteria selected for the site can only be judged qualitatively. Thus, the value of assigned one when the concerned criteria is favorable with respect to the other one. The other side assigning the value as 0.5. Such method of assigning the value also eliminates the need to normalize the matrix further. After the local priorities are developed, the final model synthesis or overall global priorities are developed, the alternative with the higher one of the overall priority indicates a better option for the goal. For our case, Site 1 proved suited site among the two options. Yeah,
Yeah, next slide, please. Yeah, thanks. So what we did after Mr. Akhil did the statistical analysis and after choosing the site 1, so we went to this place and we found there is this small pond which is quite adjacent to our site. So the name of that place is Port Balwal. So let's call it site 1 for the better understanding of the huge audience. So what we collected some water samples from various depths and various places, and the average values of these contaminants which we found in this water from this still pond was like it has like some 94 ppm of ammonia, BOD, and 1220 of COD, and all these were some initial characteristics. So what we concluded was that this is due to the presence of this unengineered landfill site near Port Balwal, and all this leachate, it is somewhere other way finding its way to this pond. And next slide, please. Yeah. So what we did was we strategically brought some wastewater. Now this wastewater will intrinsically have bacteria and microalgae in it. So what we did, you can see in the leftmost picture, we just cut off the oxygen. So what could only grow was the autotrophs. So you can notice the difference in the second picture. That is like this wastewater is now turning green, which indicates that there is no good growth of algae in it. And then we just transferred them into the flask. Now this culture which dominantly had bacteria in it, now it has a symbiotic culture of algae and bacteria. And now this algae bacterial consortia we analyzed for like a couple of months, giving it little to higher doses of all these nutrients and contaminants we wanted to remove, and we basically acclimatized this culture for our purpose, for our treatment. And then we just transferred this into a reactor, and then we just carried out a continuous preparation. You can go to the next slide and I will just finish in a minute. Yeah, so this is the little setup we have at our lab. You can see the left reactor, it is the reactor 1 aerobic process with the membrane is happening here, and the reactor 2 on the right side of it, it is the reactor 2 where the anaerobic process is happening. Here next slide please. There we have some results. Yeah, so you can see that initially what we did was in the flask level study, we acclimatized our algal bacterial culture for ammonia removal of like 40 to 50 ppm, and then nitrate removal of up to like 50 ppm. So this was at the batch level study, and you can see in the last picture, it is the green color here is indicating the algal part, and the black color is here is, or the boundary around it is representing the bacterial part. So this is the algal bacterial consortia, which is basically taking out the treatment of these contaminants. Next slide, please.
Possibly summarize as much as possible, please.
Yes. Yeah, this may be the second last slide itself. So after running it into the reactor 1 and reactor 2 at an HRT of 6 hours, what we could find in the effluent that this ammonia, which was initially around 70 to 80, is now 1. The nitrate is almost completely removed. The BOD and COD are more than 90% removed. And along with that, the surfactants and the phenols, which after the COVID-19 pandemic were doubled in the wastewater streams. It has also effectively removed these. And the theme, which is the main theme of this today's session, that the iron and the manganese, the heavy metals, which are the emerging contaminants in the water and wastewater, these are also removed. The removal efficiency was more than 70%. So we could say that this algal bacterial culture, the algae will provide it better resistivity and adaptability, whereas the bacteria, as usual, will do the job of the treatment. So here we are working on these algal bacterial novel cultures to treat the wastewater for any type of contaminants which we'll have. Thank you.
Very informative presentation. We'll be moving on to the next presentation, but you please leave questions in the Q&A box if you have any. I'm sure the speakers will try their best to answer you in the chat box, in the Q&A box. We move now on to Sabry Wahba, who will be presenting on the assessment of harmful algae as an emerging pollutant of domestic water supply from rainwater harvesting facilities in the Sudan. We hope that you really listen, because this should be quite an interesting paper. Thank you. Over to you.
Good afternoon for everyone. My presentation, assessment of harmful algae as an emerging pollutant and domestic water supply from rainwater harvesting facilities in Sudan. Next, please. The rural population in Sudan represents around 67% of the total population. Unfortunately, 55 lives in area apart from the Nile system. They lack drinking water sources. Considerable percentage of this population depends on service rainwater harvesting from Hafir. What is Hafir? Hafir is a shallow water pond and the earth dam reservoirs for domestic and drinking water supply. It is clear in the photo and the slides that's including different activities in these sites as a source of drinking, agriculture, and domestic animals drinking water source. So they add some contaminant like ammonia, nitrogen, phosphorus, everything. According to this condition, certain environmental conditions like warming and excess of nitrogen and phosphorus in water bodies can intensely algae growth, causing algal blooms. Algal blooms may be caused by organisms of blue-green algae, which is characterized by the production of toxins, which has a very harmful effect on human health consumed. Next, please. So the aim of this paper, this presentation, to classify types of algae, genera, presented and known as toxin-producing algae. Water samples were collected during the two seasons, wet and dry season, that's rainy season and the other season to collect the water from 11 sites of different 5 states in Sudan, Gezira, Khartoum, North Kordofan, Gadaref, and Sinnar. Turbidity was ranged from 13.9 NTU to 3,000 68 NTU. It means that maybe due to the growth of algae and turbidity caused by the activity around the sampling site. Next, please. As we see, the different sites were dominated by blue-green algae. They reached to be 96% in some sites, dominated by Anabina, Merismopedia, Oscillatoria, Cylindrospermum, different organisms. These genera are known as toxin-producing. Next, please. As you see, that's reached to be not only that's the percentage content, but the problem it is represented as organism primarily. Organism, it means that coloniform or filament that have a lot of millions of cells content, which are restricted and known as toxin producing. So that's the problem, not only toxin producing of blue-green algae. The problem is according to the morphological character, it has a gelatinous sheath. It may be as a shelter for other harmful organisms like pathogenic parasites or pathogenic bacteria. So that's not only the toxicity or toxin producing as microcystin and a toxin and different kind of toxins found in the organism, but also as a shelter for other microorganisms, which may be a very harmful effect on the health impact of the human rather. These sites are characterized, different sites are characterized by the activity of pastoralism, agriculture, mining, and urbanization according to each site. Next, please. Concludes that Sudanese are at high risk of contacting waterborne diseases according to these sites. Protection of surface rainwater harvesting facilities from pollution by establishing on-site water treatment units is a must. Comprehensive water quality monitoring is necessary to improve natural source management. Monitoring of toxins produced by cyanobacteria or cyanotoxins produced by blue-green algae is a very important and necessary. Collaborative efforts are encouraged at both international and national levels to be secreted. Sustainable water resources management capacity must be community engaged and political activity on local and international side. Next, please. Finally, I'd like to thank my colleagues, Dr. Mona Musnid, Dr. Wafaq Mahmoud from Sudanese sites, and I'd like to appreciate the effort done by IWRA and UNESCO to give us the opportunity to represent this article. Thanks a lot for moderator and for audience.
Thank you very much for that interesting speech and talk. The next speaker is having some technical difficulties, so we'll move to the following speaker, which is Surikanta, who will be presenting some really interesting information on an overview of endocrine disrupting compounds in drinking water and human health. If I can remind all the speakers, there might be questions in the Q&A box, and please, if you have the opportunity, go to the Q&A box and answer some of those questions so that we have time later on for a number of panel discussions. And over to you, Suryan.
Thank you, Robert. Good morning, good afternoon, good evening, depending on which part of the world you are in. And I thank the organizers for giving this opportunity to present this topic. So this is a brief overview of endocrine disrupting compounds in drinking water and specifically related to human health. And next slide. So access to safe water is paramount in determining environmental sustainability, public health, and economic prosperity. Endocrine disrupting compounds, which are short form EDC, are an environmental contaminant of emerging concern which threatens the safety of drinking water. EDCs are emerging contaminants that have accumulated in the water at concentration level that have been determined to be significant to human and animals. Several compounds belong to this family. There are some natural substances like female hormones like estrone, estradiol, and estriol. There are some synthetic chemicals included in the EDC and some pesticides which are used in agriculture field, pharmaceuticals, and plastic derived compounds, that is BPA mostly. And the purpose of this paper is to compile important aspects of EDCs, especially human health effects. Next slide. So I made a literature search and to see the recent publications and which revealed that the potential health issues of EDCs are not fully understood yet due to the scarce research on their exposure and associated risks by drinking water consumption. Literature search included EDCs, contamination and accumulation in water, their toxicity and exposure risk to human. And the left side of the picture explains the sources of these EDCs. From hospitals and pharmaceutical industry, we have the medicines or pharmaceutical compounds. There are many other air pollutants also. And from agriculture field, we have pesticides. And from wastewater treatment plants also, we have chemicals. And from plastic toys used by children, there are BPAs. So these contribute to the EDCs. And on the right side, the picture, this is a mechanism action of mostly it affects the organs which are producing hormones inside our body. So it will be explained later. Next slide. So what we know about EDCs. Many EDCs have been identified in significant amounts in different water matrices, including drinking water, thus increasing the possibility of entering a food chain. And in general, EDCs interfere with the endocrine system or the hormone system of our body, particularly the hormone signals by antagonizing the modes of action and mechanisms of endogenous hormones, especially through nuclear receptors. The disrupted endocrine system thus causes effects in exposed individuals and populations ranging from acute to chronic diseases, namely metabolic syndromes, reproductive abnormalities, behavioral changes, disrupted fetal development and growth, and it can go all the way to cancer also. And EDCs are not easily removed from the water through conventional treatment processes offered by water or sewage treatment plants. Thus, advanced removal technologies could present more appropriate removal pathways to remove EDCs from drinking water. Next slide. So owing to the diverse physiochemical properties of various endocrine disrupting chemicals, several processes can be applied as treatment technologies and to obtain different removal efficiencies. Different methods like bioabsorption, adsorption, advanced oxidation, membrane filtration, biodegradation have been investigated as suitable treatment pathways for removal of EDCs. And several EDCs have been identified in the treating drinking water supply worldwide, particularly in the tap water in the concentration range 0.2 to 5,500 or more than 5,500 nanogram per liter, with maximum concentration of 28,000 nanogram per liter detected in drinking water from the wells in India. So the World Health Organization has revealed that the WHO guidelines for drinking water quality are inadequate based on the current exposure levels of EDCs in drinking water. Next. So I'm concluding this one, integrating preventive measures with a multi-barrier approach to safe drinking water is highly challenging because of the relatively low public awareness and political responsibility, as well as the nature and characteristics of EDCs themselves. Further progress on detection, complete health hazards, and removal of EDCs from drinking water are need of the hour. WHO guideline from drinking water quality is now receiving rolling updates as and when new data emerge. The latest guideline is 4th edition with addenda published in 2022. EDCs are also present in air and food. The total intake from all sources is the deciding factor for human health effects. So a holistic approach to this emerging issue is needed. Thank you.
Thank you very much for that very interesting presentation. We've managed to solve some of the background issues in technology, and we'd like to move on to the previous speaker, which is Sylvia Cruz. Sylvia will be presenting a interesting presentation on soil aquifer treatment application to improve the chemical quality and increase the quantity of groundwater. As mentioned before, if you have any questions, please type them into the QA box and the speakers will do their best to try to answer you there. Sylvia.
Thank you for the introduction and good morning to everyone. Next slide, please. We know that groundwater currently is at risk and there is an increasing demand of water because of the increase in population, but also with the related increased uses in agricultural or industrial areas. Another important issue related to groundwater is not only the low quantity, but also the quality. In this case, depending on the water that is infiltrated through the aquifers, it can bring a lot of variety of contaminants with different chemical properties. We know that this pollution could be removed, but this is costly. And as wastewater treatment plants are not intended to remove these pollutants, reclamation technologies in an additional step are needed. So another important issue to face is to know in more detail or more reliable the quantity of the water that we already have worldwide in our groundwater bodies. Next slide, please. So how could we improve this status of groundwater? Related to the quantity, we could use managed aquifer recharge to increase this quantity in a safer way and very targeted because we know exactly in which aquifer we are working in. But pollution attenuation is still an important issue. So if we use MAR or soil aquifer treatment technologies to increment the groundwater, we have to keep in mind that maybe other approaches should be needed in order to remove this pollution. For instance, the approach to use a reactive barrier in the area of infiltration in order to improve the natural degradation capacity of the soil aquifer system. So if we obtain a good water quality, then we could use all this recharged water for further purposes, for instance, even to produce drinking water. Next slide, please. So here I'm going to present one study that we performed in our pilot soil aquifer treatment system in the wastewater treatment plant of Palamós in Girona in Spain, where we are introducing the secondary effluent of the wastewater treatment plant into an area of infiltration that in one case is only made up of sand, but other infiltration areas, in this case selected, were compost or wood chips to improve this natural removal of the microorganisms that are in this area. As you can see here, the pilot is composed by 6 identical systems, and we have piezometers to gather water at different depths and at different distances from the infiltration, and at the end of these channels mimicking the aquifer. Next slide, please. So in this study, we look for as many as possible contaminants of emerging concern. And so we applied liquid chromatography attached to high resolution mass spectrometry to identify, but also to semi-quantify the occurrence of these pollutants. In fact, in the whole study, in all the samples we gathered during two periods of research, we identify 124 different chemicals, not only parent, but also a lot of metabolites of them, belonging to different classes. Here are some, for example, pharmaceuticals, practice additive, UV filters, illicit drugs, and a lot more. Please, next. So, in these 2 research events we performed, one was in June, and we used research approach by continuous recharge. And in October, we performed more or less the same, but with pulse recharge, 2 hours of infiltration and 2 hours of stop infiltration, and so on. What we observed in the whole lot of contamination is that the wastewater treatment plant is degrading a lot of pollutants. That is very good, very good news. And what we observe is that in June, we've got a higher pollution in comparison with October. This is because this wastewater treatment plant is located in a very touristic area in the Costa Brava, and then the population during this summertime doubles that of winter. So in this case, we identify higher concentration and higher frequency of illicit drugs, for instance, cocaine or methadone, and also nicotine, and so on, very related to human use. We observe also that the degradation of pollution was compound dependent. And in next slide, I will go in deep in this issue. And no, please, first, okay, thank you. We observe also that when we use the different compounds in this barrier, compared to the sun system in the infiltration, the degradation of compounds were quite low. It was improved when we add compost to this barrier, and it was even better, the extent of degradation when we use wood chips. What we observe also is that when we use the system on their monitoring by on their pulse recharge, we observe a higher degradation than if we use a continuous flow through the infiltration system. Next slide. So what we observe is that if we use the system in the continuous recharge, we could degrade around 37% sorry, of the pollutants. But if we use a pulse system, sun didn't work. So it's a very important observation. And in the case of the removal of individual compounds, we observe quite different behaviors. For instance, in the case of the benzotriazole UV blockers and the derivatives compounds, we observe that in the sun, at the end of this, the recharge system, the MARS system, we have a higher concentration. But in the other case where organic material was included into the reactive barrier, we observe a really important decrease in both, particularly in the wood chips one. With respect to carbamazepine, that that is a very recalcitrant compound in removal technologies. Not only carbamazepine, but also its degradation products or metabolites, human metabolites mainly, reduced only when we use organic material into the barrier, but not in sand. And in particular, this group of carbamazepine-related compounds were higher degraded in the wood chips barrier. Other compounds such as the pharmaceutical lorazepam or the diclofenac or even some pesticides only could reduce in the barrier with wood chips, and others, in the case of other pharmaceuticals and also some industrial additives, only could reduce in compost barrier. Next slide. So these results bring to these conclusions that the reduction of these contaminants of concern demonstrated that the implementation of this soil aquifer treatment system holds a really great potential to attenuate the toxic effects or risk associated to all these contaminant loads in the wastewater treatment plant's effluents. So this will allow the safe potential use of these aquifer recharge schemes and could be more promoted into let's say into the society. So the degradation observed suggests that the reactive barrier composed of a mixture of diverse material could be more efficient to degrade this wide range of pollutants with a very different physicochemical properties. And finally, that if we achieve a very functional such system with the capacity to reduce a wide number of these contaminants of emerging concern from the recharge water, whatever it is, from a wastewater treatment plant or even from the river, will be perceived as a really natural-based and cost-effective solution to face current issues related to water scarcity, to aquifer recharge, all these in connection with circular economy in the support of groundwater water reuse policies. Next slide. And thank you all for your attention.
Thank you, Sylvia. That was very interesting, and I hopefully will help people start looking at solutions for reduction of emerging pollutants. We'll be moving on now to a piece of work in Kenya. Kalin Karimi will be talking about groundwater contamination with sorry about that, solmethoxylol and trimethyl trim and spread drug resistant of E. coli in informal sediments in Kenya. Sorry about that, Kalin, and the floor is yours.
Good afternoon from Kenya. Good afternoon, good morning, good evening from wherever you're listening to. My name is Kalin Karimi. I work at the Department of Global and Public Health at the University of Nairobi, Kenya. Our work is on groundwater contamination with sulfamethoxazole and trimethoprim. This is an antibiotic, and the spread of resistant Escherichia coli in informal settlements in Kenya. Our work was anchored in a project that was at the Department of Geology in the same university. Part of the context, the purpose of this study, it's part of a doctoral study that investigated contamination of groundwater with sulfamethoxazole. We started with mapping out the prevalence of antibiotic use in the area, which was found to be at 43%. This was occasioned by misuse. We also studied misuse and the proper disposal of the antibiotics. And the resultant of disposal makes it difficult to determine the cause of resistance in the environment, the contamination and the resistance. A little bit of the context that informal settlements, particularly in this area, are densely populated, and therefore population is higher. And these people rely very highly on groundwater to supplement on the water that the availability of or inavailability of water provided by the municipal council in the country or in the county. So reliance puts on groundwater, puts these people or the population at a risk of antibiotic resistance. So these antibiotics, the sulfamethoxazole and trimethoprim, are mostly used for treatment or prophylaxis or prevention of infection among HIV patients. And in this study area, the HIV prevalence is quite high, higher than the national figure. Next slide, please. Let's go to the next. Okay, so the methodology, what we did, we actually mapped out groundwater sources, which were 180. So the map that has all the groundwater sources is very crowded. So out of the 180, we picked randomly selected 49 water points cross-sectionally, and then we analyzed for sulfamethoxazole and trimethoprim in the water samples that were collected. And then we did antibiotic sensitivity using the Kibi-Bauer method to determine resistance against E. coli. Next slide, please. So based on this map, we had, let's go to the next slide, yes. We had the results as follows. We were able to pick or the red or orange, okay, some of us were colorblind. The red is the spots or the water points where the antibiotic sulfamethoxazole was detected. We did detection for the antibiotic. It's used as a combination, but it was separated. The spots with red are where sulfamethoxazole was detected, and the spots in yellow is where the antibiotic resistant E. coli were spotted. To note is that the points where the antibiotic was detected is way separate. It's not the points where the detection was the detection of the resistant E. coli was done. And to be more specific, near where the yellow is featuring, where we have the inhibition zone, we have a blue patch, and that when you look on the map of the entire area is a water treatment, the Kisumu Sewerage Wastage Recycling Center. So that could be part of the problem, or part of why we detected the resistant bacteria in that spot. That is yet to be investigated using, of course, design or models. Next slide is on the policy implication. So the amount of antibiotics that cause resistance in the environment is largely unknown. In literature, wherever you have looked, it's largely unknown. So that is a red flag. If it's a lot of antibiotics or little antibiotics that are required to cause resistance in the environment. So the antibiotic, specifically this that is being used by the HIV patients, must be closely monitored for further investigation and look for triggers. Thank you.
It was very interesting. We'll be moving on to the next speaker and hopefully have a little bit of time for questions at the end. But please type your questions in the Q&A box, and I'm sure the speakers will take the opportunity to open the Q&A box and try to answer the questions where possible. We'll move on to Enrique Escalante's presentation on monitored and intentional recharge, a conceptual model to draft water quality regulations for managed aquifer recharge and water reuse. And hopefully we'll be able to come back to Jane shortly. So Enrique, over to you.
Good morning, ladies and gentlemen, and expressing my gratitude to UNESCO and IWRA for giving us this opportunity to introduce this new concept, what we have called MIR, or Monitored and Intentional Recharge, emerging from the Marsolute H 2020 project. Next, please. Okay, the MIR concept is a conceptual model to draft the managed aquifer recharge and, in general, the water reuse guidelines documents, specifically adaptive to its environmental circumstances and its country's regulations in the world. It is composed by a set of 9 different blocks that guarantee a technical success. after its application. It's really useful to face up water quality improvement and the emerging compounds phasing up. And it is also based in an intense and planned monitoring, what we call the hydrodynamic monitoring, what is becoming key for water quality and water security improvements. So in short, MIR is a conceptual model to draft managed aquifer recharge guiding documents and water reuse documents as well. Can we pass to the next slide, please? Okay, the methodology has been a very intensive, very detailed review of the 22 existing regulations and guidelines about MAR and water reuse. What means all of them that we have been able to gather, and paying special attention to monitoring guidelines and risk impact-based analysis. Next, please. After that, we have established what was the most important and the less important in the 22 different documents, and studied very carefully, establishing one appraisal according to their degree of development and scoring what was the most important and the less important, and specifically adaptive to the new world. Next, please. This is the skeleton of the MIR conceptual model. It is composed by 9 different blocks. It is a minimum composition because there are some more and specifically adaptive circumstances that could cause a certain enlargement of the MIR conceptual model. Next, please. So the blocks that are included as different chapters in this model are the water sources, the environmental conditions, the MAR or water reuse technologies, the sensoric used for an hydrodynamic monitoring, the extensive monitoring and wise monitoring, the final use of the water, some analytical issues specifically related to the topic of this conference, and the risk assessment. There is a 9th block for others, what every technician or scientific could include. Next, please. So different schemes have been provided for the hydrogeological literature for all interested authors to pay attention on them and to enlarge this information. Next, please. So this is the development of each block. It is a summary, of course. It is a recipe style test in order to not forget any important issues to be included when drafting any guideline document. I repeat again, for MAR or for water reuse. Next, please. And jumping into the takeaway messages, we can conclude that the MIR conceptual model is a list of elements to consider when drafting guidelines and regulations about MAR and water reuse. It encourages a tailored approach based on the specific context for each country and regulations for each specific site when we are trying it to be applied. MIR stresses the importance of alternative water sources and increase the awareness of water quality. The concept also entails water quality and water security improvement based specifically in planned monitoring activities. This concept has been already proposed to Peru and Niger water authorities. They are considering seriously to apply it, and we hope in the future to propose it to the European Commission decision makers. And the last slide, please. And next, please. If you want to enlarge this presentation, there are the results from the ISMAR 11 conference and the recent article published in the Water Journal. Thank you very much for your kind attention.
Thank you, Enrique. That was very interesting. And of course, the managed aquifer recharge and intentional recharge is going to be more and more important with climate change adaptation. We're now moving on to Jane Thrasher, who will be presenting on the development of a GIS-based tool for the prioritization of sites with potential sources of PFAS impact to the water environment. Jane.
Today I'm going to talk to you about the development of a GIS-based tool for prioritization of potential PFAS sites. And this is some work that we've been doing for the United Kingdom Environment Agency. with my colleagues in Jacobs in the UK here. Next slide. So a bit of background of why we've been doing the project. The United Kingdom does a program of surveillance monitoring of both surface water and groundwater, and these maps are showing you some of the results for PFAS or PFOS in surface water and PFAS more widely in groundwater. And in essence, this surveillance monitoring has shown the ubiquitous presence of PFOS in surface water, often present above the very stringent environmental quality standard of 0.65 nanograms per litre. It's widespread, but they're not necessarily particularly high levels in most of the places it's been looked at. Likewise, with the groundwater, you can see there's widespread distribution, possibly more in some areas than others. And again, generally low level, but we do know that in some local places, there is PFAS present in raw waters that drinking water supplies are taken from. So looking at these maps, identified the need for further research and investigative work to evaluate the sources contributing to the widespread PFAS in the environment. We have the next slide, please. So basically, what we are trying to look at is to understand where the potential source sites for PFAS might be in the UK that are influencing surface water and groundwater, or should I say actually in England, and by looking at potential PFAS sources. So I hope everyone's familiar with some of the issues associated with PFAS. The infographic here shows some of the sort of sources, pathways, receptors that we have. The fundamental problem is that PFAS have applications in a wide variety of consumer products and industrial applications because of their properties. They've been in use for a long time, since the 1950s. They're persistent, they're mobile, they're bioaccumulative, they're potentially toxic, and therefore they continue to be a problem for ongoing time. There are thousands of potential source sites in England where PFAS might have been lost to the environment, and part of the question is which are the ones which are having the biggest impact. And the sort of sites we're talking about are sites where PFAS containing firefighting foam has been used in firefighting training, but also potentially in fire protection and prevention. So for example, in fire suppression systems for oil depots, etc. Then thinking about places where PFAS might have been used in industrial applications. So for example, mist suppression or specialist coatings. And then of course, there's the ongoing problem of PFAS deriving from the intentional or otherwise disposal of materials containing PFAS. So the wastewater effluent that we all flush down the drain from the washing things which are treated with PFAS or use in cosmetics, etc. The PFAS disposed to landfill and just run off from urban areas. And the big question we've got is how do you prioritize these sites for further assessment and effective regulation in a consistent and systematic manner, rather than simply focusing on the known high profile, easy to spot sites. Next slide, please. So the approach we've taken to this is to develop the PFAS risk prioritization tool. The objective being to develop a methodology to identify the high risk sites to enable prioritization of effort. And this is a national GIS-based tool to use to map and prioritize sites. We've produced something called the PFAS Risk Explorer, which uses a GIS approach with Esri ArcGIS and uses multi-criteria analysis to rank source sites based on environmental setting using national data sets, including water quality data, site types, and information that we've gathered about the environmental setting to allow us to assess the relative risk of different sites as well as the presence of them. And our view is that this approach of presumptive source mapping, so thinking that any site where PFAS might have been used could potentially be a source of PFAS, helps to rapid and systematic identification of potential exposure sources. Next slide, please. So one of the key things that we've had to do for this is to map potential source sites across the whole of England. And I think one of the most important things to bear in mind here that we're trying to make it national and consistent. So we've used a variety of data sets, some of them existing data sets that were already there, some using web scouring to build new data sets from information that might be there, some from information held by the regulators and some that were purchased. And we've ended up with a mixture of coordinate points, addresses and polygons, and had to convert these to polygons to work the system. And this table here shows a selection of the sort of sites that we've included in our model and the numbers of sites. And I guess what will stand out from that partly is, well, A, there's an awful lot of air transport sites of different sorts of airports, airfields, etc. It's not just the big ones, there's lots of others as well. Lots and lots of fire stations, municipal, other. The landfills, one of the reasons that's so big is that we have a very good data set of the locations of historical landfills, as well as the permitted and current. So most of those are older ones. But there's a wide range of sites here. Next. Another of the elements of the tool that we've got are these environmental setting heat maps. And this is just a little illustration of that, where we have good mapping that we use to understand the national risk for source protection zones for where our drinking water abstractions are, for example, and things like groundwater vulnerability. So where the sensitive aquifers are exposed at the surface, very vulnerable to pollution, or where there may be alluvium or something over it, so there's less of an exposure risk. We've used a weighted scoring system to pull these together, do multi-criteria analysis and come up with a general heat map for the environmental setting for groundwater, with the lighter areas showing the higher risk. And we can then use that to combine together to score the different sites for it. Next. And this is all integrated into our GIS portal, which we can use to explore the data, to zoom in on particular areas around the country and understand what might be going on here. So we can visualize the data. This is showing our surface water maps with buffers around that. The black polygons are showing where our potential source sites might be in that area. And the little pie charts are showing, summarizing some of the water quality data monitoring that we've got. And you can see how they come together, and you can see where the data fits in relation to the sites. Then the next one, we can also use it to analyze on a wider scale. Sorry, I was looking at the next picture. We can analyze on a wider scale. So we can run little reports to see how many sites might be in a water resource zone and what impacts there might be there, which ones have more of the sites that we've mapped in it. And we can produce reports and outcomes from it. And the final slide. So what the outcome of all of this is, we've mapped around 30,000 sites which are potential PFAS sources. And it's absolutely crucial to recognize that this is presumptive mapping. We don't know that these contain PFAS or impacted by PFAS. They're just the sort of sites that could have the potential to be PFAS sources. Using our environmental risk mapping, we can see that more than half of these sites have scores indicating high risk scores, because they're in sensitive locations which are vulnerable to contamination, for example, due to the proximity to surface water or to groundwater. But what's really important to understand is the model can't be used to identify if any of these sites present unacceptable risks. They need site-specific interpretation, review, they need monitoring data, they need a closer look. But what it can be used for by the regulators and stakeholders is the first step in identifying and prioritizing sites for further desk-based study or site investigation. And actually, I think one of the things this study shows is the magnitude of the challenge which is facing regulators and stakeholders associated with identifying and managing PFAS sources, including these legacy sources from past activities. So the next steps on our work is model enhancement and refinement and improved user interface to help people use it better. Further case studies and sensitivity testing to check that we're doing the right things and pulling out the right sites, and also further work to refine differentiating source sites. And final slide, just to acknowledge the people involved within this. The work has been funded by the United Kingdom Department for Environment, Food and Rural Affairs and the Environment Agency. The steering group and the agency have been particularly involved in helping us develop this. Angela Haslam, Helen Pickering, Michael Hughes, and many others as well. And in Jacob's key team involved in this are Russell, Francesca, Yoland, myself, and many, many others. Thank you very much, and apologize for the technical difficulties within all of that.
Thank you very much, Jane. We'd like to move on quickly now. I'd like to introduce our co-moderator, Nikola, who will be asking general questions from the audience, from the Q&A box, And if the panelists can please answer the question assigned to you, that would be fantastic. So Nikola, please.
Hello, thank you, Rob. Question for Jane. Did you also consider the effects of mixtures of chemicals in your GIS analysis? For example, the proximity of other emission hotspots, such as hospitals or agriculture, to the PFAS source sites? Jane, please.
Not particularly, no. We have been focusing on PFAS sites. So in terms of mixtures of chemicals, no, we haven't particularly, I think is probably a simple answer to that one. We are certainly conscious of there being a whole range of different PFAS sites, such as agriculture, that we should be considering within what we're doing. Does that help? Sorry.
I hope it helps. Thank you, Jane. Let's move forward. So a question repeated 2 times already. So I believe it's for Sabry, the second presenter. Can you say something about haffirs in Sudan? Are they lined up or not? And what is the type of soil type in the areas?
Unfortunately, it is not lined because it is natural haffirs. It is very shallow ponds naturally. The soils around may be more or less it be clay, sometimes a mixture between sand and clay, according to the topography and the area of the pond or haffirs.
Okay, thank you.
Thanks.
And I believe there are 3 questions actually for Sylvia. I'm not quite sure. What about the contaminant chloride in groundwater and drink water? What about the perchloride and pesticide metabolites? Sylvia?
I'm not sure if this is a question for me, but perchloride we didn't analyze, and some pesticides we look at them. But this is in the fact in the beginning we use this pilot to follow the degradation of the main components in the wastewater secondary effluent, because this is an urban area. Not necessarily there is a lot of pesticides and so on. So the pesticides load was not so important as pharmaceutical and personal care products. This is why we focus most on this type of pollutants. But in the suspect screening and non-target analysis, you can look for metabolites of pesticides, but you have to use particular databases to identify the profiles or the features obtained in order to identify this pesticide. But so far, we didn't do that because we didn't obtain a high concentration of lot of pesticides, because this is not a place where they are used to be identified, present.
Okay, thank you. And maybe let's see, again for Jane, please, how does your tool catch up to quickly changing landscape? For example, if certain urban establishments suddenly were abandoned or replaced, and does your tool capture the seasonality differences of the risks across the area?
I'm afraid we're not that clever. We have to work with what is humanly possible to deal with it. So the changing landscape is actually one of the challenges, and really, I think probably in every country, we are, the best we can do is based on the data we have, and we do not have good geographic data sets for everything, even as we are at the moment, and certainly not for what was happening 10 years, 20, 15 years ago, when people didn't know that PFAS was an issue. So it is a big challenge to keep up with it. So it's a crude tool, it's not accurate. In terms of seasonality differences, I think probably in the UK, the seasonality isn't, we get rainstorms in summer as well as in winter. So seasonal differences aren't so important to us here. with the way we do it. So we don't capture seasonal differences in it.
Thank you.
But thank you for the questions.
Sure. Thank you all for your questions. I believe that's it for now. There are some questions that are related, that are rather general, so we will forward them directly to the panelists and they will be answered later on. Bob, I think that's all from my side. Thank you.
Thank you very much. Well, I've thought this was a wonderful collection of papers and presentations on emergent pollutants in groundwater. I'd like to thank all of the speakers for the insightful information that you've shared with us, and also for dealing with the technical issues in the background when they've occurred. Importantly, I'd like to thank the team from UNESCO and the IWRA who have worked tirelessly in the background to make this a successful conference, and we hope that you continue on with the conference and further sessions. I would like to thank my co-moderator and also Dahlia, who's been doing all the rapporteuring and will be presenting the outcomes and a summary of all of our papers later on in the conference. Once again, as Nikola just said, we'll collect written responses from the presenters to any remaining questions that we have received, and we'll be placing those on the conference website. Also remember that the conference is recorded, and so if you've missed something, or if because we had to move back and forth, you missed a talk that you were looking for, please go back on the recording and you'll find the talks within the session. Also, there's an excellent selection of submitted conference posters online at www.iwraonlineconference.org. And these posters can be found under the posters menu. If you have any questions on these posters, you can email the IWRA at online.conference@iwra.org, and we'll continue to contact the posters authors to respond to your queries. And also, as mentioned before, with regards to the PowerPoint presentations you've just seen, these will also be made available soon on the conference website, so that you'll be able to go back and review those as well. So with that, I would like to thank again all the speakers and all the organizers for this session. It's been a wonderful sharing of knowledge and information that can help to inform policy in the future. And I'd like to pass along to the IWRA for any last minute points before we close this session.
No, thank you, Bob. Thank you, Nikola, and all the panelists. I think it was a very interesting session. So we are now moving on and preparing for the next session to start at 12:15 Central European Time. Thank you.
Thank you to everyone.
Thank you.